Okay, in this video, we're going to continue our discussion of intermolecular forces with a discussion of hydrogen bonding. So hydrogen bonding is only going to occur when you have one of three types of bonds. You either need HO bonds, HF bonds, or HN bonds. So these molecules have very strong intermolecular forces. And because they're so strong, we give them their own name. We call them hydrogen bonding. The reasons for them are related to the idea of dipole-dipole forces in general. But I think it's a reasonable question to ask of, why do these get a special name? Why are they so much stronger? Well, there are some reasons for this. First is the fact that the hydrogen atom is very small. Remember, it only has one proton and one electron. And oxygen, fluorine, and nitrogen are in the second period. So they're also going to be relatively small. Because these are so small, both atoms are so small, they can get really close together. And remember, these are all electrostatic interactions, so once they get really small, they can get close to other molecules. So these are special first because of their smallness. Very small, which means can get close. And once they can get close, they've got a strong interaction. Because remember with electrostatic stuff, as things get further away, they don't interact as well. So with electrostatic interactions, it's important. The closer you can get, the stronger that attraction can be. Now, the other part is that there's a fairly large electronegativity difference. Electronegativity difference. So without this part, the size wouldn't matter. So, in these cases, nitrogen, fluorine, and oxygen are all fairly electronegative, so they really like to hold on to electrons. Hydrogen isn't nearly as electronegative, so it gives them a strong partial negative charge on the oxygen, fluorine, and nitrogen, and a strong partial positive charge on the hydrogen. This is why, for example, the hydrogen-carbon bond can't hydrogen bond. When hydrogen's bonded to carbon, they have very similar electronegativities. So the electrons aren't spread out near as much. They aren't really strong on one end. So even though carbon is also relatively small, like oxygen, fluorine, and nitrogen, it's a little bit bigger, but not much, it doesn't have that electronegativity difference, so it can't hydrogen bond. As you go down the periodic table, like let's say instead of fluorine, you took chlorine. Well, chlorine has an entire other period, so it's going to have a lot more size, so it's not going to be nearly as close, so it can't hydrogen bond. It also doesn't have quite as much of an electronegativity difference because chlorine isn't as electronegative as fluorine, but the main part is the fact that chlorine is just larger, so we're not going to see it with it. So these bonds come up a lot because they're just so strong, so we'll use them a lot with understanding interactions. So for example, our molecule water has hydrogen bonding because our oxygen is bonded to a hydrogen directly. Now, it's important to note that they have to be bonded to each other directly. So this has hydrogen bonding. But we drew a molecule just a moment ago that doesn't. So let's take the molecule formaldehyde. Formaldehyde has an oxygen and it has a hydrogen, but they're not connected together. Because they're not connected together, no hydrogen bonding occurs. Now what this means is if the molecule, instead of looking like this, looks like this, CH2O, you have to do the Lewis structure to make sure you know, is that hydrogen connected directly to an oxygen, fluorine, or nitrogen? Because I'll be the first to say, asking does CH2O have hydrogen bonding, we'll get a number of students say, well, yeah, there's an oxygen and a hydrogen, they look even close to each other in the molecule. But they're not directly bonded if you do the Lewis structure. So therefore, no hydrogen bonding. So to make sure to pay attention to that. Now, we said they're really strong. It's important to note that does not mean they are as strong as covalent bonds. So a hydrogen bond will usually be around 2 to 5% of the strength of a covalent bond. Now, obviously different covalent bonds are different strength, different hydrogen bonds are different strength, but in general, our covalent bonds are going to be much stronger. So even though hydrogen bonds are much stronger than other dipole-dipole forces, which are much stronger than a lot of dispersion forces, our covalent bonds are still a lot stronger than all of those. And that's a good thing to keep in mind. Now, with all of these, this is always a relative thing. So for example, if you have a molecule that has, let's say something like a protein that has hundreds of atoms in it, probably more than hundreds, but either way, if you take really, really large molecules, like let's say you take octane. Octane has 8 carbons and it has 18 hydrogens. That molecule, if I remember right, is a liquid at room temperature, even though it only has dispersion forces. That's because it just has so many atoms that eventually, with enough molar mass, the dispersion force gets really strong. And that can be stronger than some really weak dipole-dipole interactions. So in general, our trend is dispersion is our weakest, and then we have dipole-dipole, and then we have hydrogen bonding. But this is for cases where the molecules are like similar sizes, but you can take a molecule that's really, really large, and then a molecule with a really weak dipole-dipole force, because maybe the polarity difference is only small, and the dispersion force could end up being stronger in that case. Now, I want you to understand that as a general idea, but that's the type of thing where we would need some information, like boiling points, or we would have to do some experimentation to figure out. I do not expect you to just look at 2 molecules and go, oh, octane versus formaldehyde, which is different. That's not reasonable. In cases like that, I would simply ask you, which of these has dipole-dipole forces? Or which of these only has dispersion? When you're going to compare strengths, it's going to be things that are similar enough that they're easy to compare. For example, I might ask you to compare this molecule to this molecule to this molecule. Something like that. Okay, actually, for this one, I needed to draw another. Nah, that's okay. Something like this. Here, what we know is this only has dispersion. This has dipole-dipole. And this has hydrogen bonding, and they're all somewhat similar molar masses. Bonding, not bombing. Bonding. So, my dispersion force only is going to be my weakest. My dipole only one is going to be next. And then my hydrogen bonding one is going to be my strongest. So this is if I wanted to list them from weakest to strongest intermolecular forces. But you'll notice I purposely chose molecules that had some similarities between them. I didn't ask you to compare a molecule that had 14 carbon atoms to one that only had 2 carbon atoms but also had an oxygen. Because at that point it doesn't become reasonable for you to be able to make that comparison. So, hopefully it helps out with that. And the last one we want to talk about, we're going to do just a little bit on, is we're just going to mention that ion dipole exists, basically, because we're going to talk about it more in a couple chapters when we get to solubility. So, ion dipole means that in a mixture, ions form from an ionic compound. So you take something like table salt, you put it in water. From an ionic compound, there's not supposed to be a comma there either. So in a mixture, ions from an ionic compound are attracted to polar molecules. So what that means is if I put some sodium chloride, molecules. Trying to make it a C. So if I've got some sodium and I've got some chlorine, I didn't make enough room to draw in there. We're going to try again. Because I wanted to make the sodium bigger since it's larger. So I'm remembering right. I think I got my sizes right. Wait. No, just kidding. I did that reverse. Remember, chloride minus, we added an electron. Yeah. Eraser. Yeah, there was enough erasing here. We're just going to do all that. Yep. So yeah. So chloride gained an electron. It's going to be bigger. And sodium plus is going to be smaller. What happens is the water molecules are going to arrange so that the hydrogens of water get close to the chlorine because they're more positive. Whereas for the sodium, the oxygens are going to get closer. Now I'm only drawing 2 of these. There would be more than 2. They would get surrounded by water. And it wouldn't just be in this 2-dimensional plane. It would be in all 3 dimensions. So the sodium pluses would be surrounded by oxygen. I am tired tonight. So you get the idea. So the oxygens get close to the positives, the hydrogens get close to the negatives. And so this interaction is called an ion dipole attraction. And it's going to be stronger than all three of the other intermolecular forces we've mentioned so far. So it's going to be the strongest of the ones that we've covered. So that's what leads to this. So now, how can I turn this into a question I ask you? So let's take three substances. We're going to take formaldehyde. We're going to take fluoromethane. And these are all pretty similar molar masses. And then I'm going to take hydrogen peroxide. And what I'm going to tell you is one of these is a liquid, two of them are a gas. Based on everything we just said, remember, I guess I have to mention that again. Oh, no, that's okay. We'll just talk about this since it's a test question. So if you don't know how to figure out, that's okay. We'll talk about it in a second. So between these three, which of these is going to be a liquid? So pause me and give it a try. Okay, hopefully you pause me and now you're listening. So the one that's going to be a liquid at room temperature is going to have stronger intermolecular forces because that means it has a higher boiling point. So this is effectively a question about boiling point. So in this case, here we have dipole-dipole interactions. For our fluoromethane, we're also going to have dipole-dipole because we've got carbon connected to fluorine. But notice in both these cases, the fluorine and the oxygen aren't directly connected to hydrogen. But for hydrogen peroxide, we're going to have hydrogen bonding. Since this third one has hydrogen bonding, it's going to be the one that's going to be a liquid because it's going to have the strongest intermolecular forces. IMF. So this is a way that question can be asked that admittedly is complex. Like I think that question is a challenging one that's asking you to think about, okay, what have I learned about intermolecular forces? How does this relate to, I've got three substances, which of these is a liquid? I also think it's the type of question, once I've told you, if you get asked exactly this, here are three substances, which is a liquid, this might be what you think of, but that it's about the application part of how do I think about this if the context changes a little bit, how can I do something useful with it? Do you really have to get to and engage with these ideas? So this is the last for the types of intermolecular forces. In our future videos, what we'll be talking about is what are properties that are determined based on those intermolecular forces, what happens because of them, what changes about a molecule.